The universe is expanding, that much we know. But here's the uncomfortable part. We don't know where it's going, or what's driving it. Galaxies aren't just drifting apart, they're racing away from each other faster and faster. Like cosmic dots on an inflating balloon, something unseen is pulling the fabric of space outward, stretching it with growing urgency. But what is it expanding into? Will it slow down, reverse, tear itself apart? This is a question about reality, about time, space, and what it means to exist in a universe that's quietly evolving and possibly destined for a very strange end. Let's explore the clues we've gathered so far, from the strange fingerprints left in the cosmic microwave background to competing visions of how it all might end. Expanding horizons, revisiting Hubble's discovery. In the early 20th century, astronomy was still focused mostly on our own galaxy. Many scientists believed it was the entire universe, that everything that existed was part of this one great island of stars. Some distant fuzzy patches in the sky, called nebulae, were thought to be gas clouds inside the Milky Way. The true scale of the cosmos was still hidden. But all of that changed when a man named Edwin Hubble turned his telescope toward the Andromeda Nebula. Working at Mount Wilson Observatory in California, Hubble used one of the most powerful telescopes of his time, the 100-inch Hooker telescope. In the early 1920s, he began carefully studying variable stars within Andromeda. These stars, known as Cepheid variables, have a special trait. Their brightness changes in a predictable pattern, and the time it takes them to go from bright to dim can be used to figure out how far away they are. This gave astronomers a kind of cosmic measuring stick. When Hubble calculated the distance to these stars, he made a discovery that would shake the foundations of astronomy. Andromeda was far too distant to be part of the Milky Way. It wasn't a nebula inside our galaxy. It was a galaxy of its own, a whole other system of stars, hundreds of thousands of light years across, separated from us by over 2 million light years of space. Hubble had proven that the universe was far larger than anyone had imagined. Once it was clear that other galaxies existed, astronomers started to ask another question. How are these galaxies moving? Are they drifting toward us or away from us? Are we in the center of the universe or just one point among many? To answer this, scientists turned to a tool called spectroscopy. When light from a distant galaxy passes through a prism or a diffraction grating, it spreads into a spectrum. Much like sunlight through a raindrop creates a rainbow. Within that spectrum are dark lines caused by elements in the galaxy's stars absorbing certain wavelengths of light. These lines serve as fingerprints for atoms like hydrogen, helium, and others. But if a galaxy is moving, the position of those lines can shift. If it's moving toward us, the light is squeezed, shifted toward the blue end of the spectrum. If it's moving away, the light is stretched out, shifted toward the red. This effect is known as the Doppler shift. When Hubble and his colleague, Milton Humason, examined the light from distant galaxies, they noticed something remarkable. Almost all of the galaxies were red-shifted. They weren't coming toward us. They were moving away. And not only that, the farther away a galaxy was, the faster it seemed to be receding. The pattern Hubble found was clear and simple. Distance and speed were linked. This relationship is now called Hubble's law. It meant that the universe wasn't static. It was expanding. Space itself was stretching, and the galaxies were being carried along with it, like raisins spreading apart in a rising loaf of bread. At the time, the idea of an expanding universe was hard to accept. Even Albert Einstein had originally introduced a cosmological constant into his equations to keep the universe from expanding or collapsing. He thought the universe should be balanced and still, but Hubble's discovery showed that wasn't the case. When Einstein learned about the evidence, he reportedly called the cosmological constant the biggest blunder of his life. The idea of an expanding universe was radical. It meant that if the galaxies were all moving away from each other now, then in the past, they must have been closer together. Keep going back far enough, and you'd reach a time when everything was in one place. This was the beginning of what would later be called the Big Bang Theory. The redshift became one of the most powerful tools in cosmology. It allowed astronomers to measure how far away objects were and how fast the universe was growing. Over time, more precise measurements were made, using better telescopes and more detailed spectroscopic data. The value of the Hubble constant, the rate at which the universe expands, became a central question in astronomy. Today, we can look back at galaxies so distant that their light has taken over 13 billion years to reach us. The farther we look, the more redshifted their light becomes, stretched by the expansion of space itself. In fact, some galaxies are now moving away from us faster than the speed of light, not because they're breaking the rules of physics, but because space is expanding so rapidly at those vast distances. This idea is a direct result of Hubble's work. His findings not only changed how we see the universe, but also how we understand time, space, and even the origin of everything. The Hubble constant conundrum, a tension unresolved. The Hubble constant tells us how fast the universe is expanding. If you know this number, you can estimate the size of the universe, its age, and how long ago the Big Bang happened. For decades, scientists worked to measure it more and more accurately. But something unexpected happened. As the tools became better, the numbers didn't start agreeing. They started to drift apart. The idea of the Hubble constant goes all the way back to Hubble in the 1920s. The relationship between the speeds and estimated distances of galaxies became the foundation for the Hubble constant, which describes the rate of expansion in units of kilometers per second per megaparsec. That means for every megaparsec of distance, a little over 3 million light-years, galaxies are moving away at a certain number of kilometers per second. At first, Hubble's measurements weren't very accurate. He overestimated distances, and the value he found was far too high. But that wasn't surprising. The tools he used were primitive by today's standards. Over time, as telescopes improved and scientists learned more about the stars and galaxies they were measuring, the value was refined. For many years, the goal was simply to get everyone to agree on one number, and eventually they did, or so it seemed. Things changed when different types of measurements began to give conflicting results. One of the most trusted methods involves what we see in the early universe. The Planck satellite, which mapped the cosmic microwave background, or CMB, in great detail, gave us one of the most precise measurements ever. It calculated the Hubble constant based on conditions just 380,000 years after the Big Bang. Using models of how the universe evolved from then until now, it predicted a value of about 67.4 kilometers per second per megaparsec. But then another team measured the expansion using much closer objects, type ER supernovae in nearby galaxies. These are standard candles, which allow scientists to calculate distances directly. They compared those distances with the galaxy's redshifts to get the Hubble constant in the present day. Their result came out to about 73 kilometers per second per megaparsec. That's a noticeable difference. And it's not just a matter of small errors. The numbers are far enough apart that they can't both be correct unless something important is missing from our understanding of the universe. This conflict has become known as the Hubble tension, and it hasn't gone away. In fact, the more data scientists gather, the more solid both results appear to be. Measurements from the early universe and measurements from the late universe continue to give different answers. The question now is why the two methods don't agree. One possible answer is that one or both are missing something. Maybe the models we use to go from the early universe to the present aren't quite right. Or maybe something strange happened along the way, something the models don't include. Some scientists have even suggested that dark energy might not be constant, but instead changes over time. If that's true, it would affect how the universe has expanded. Others think the problem might be in the measurements themselves. Supernova data depends on how well we understand these explosions. If their brightness changes slightly over time, or if they behave differently in the early universe than they do now, that would throw off the results. It's also possible that the galaxies being used are not typical, or that something in the dust between us and them is interfering with the light we see. Meanwhile, the early universe measurements depend heavily on a model called lambda cold dark matter, or lambda CDM. This model has done a great job of explaining many things, like the structure of the universe and the behavior of galaxies. But it also relies on certain assumptions, including that dark energy is constant and that dark matter behaves in predictable ways. If any of those assumptions are wrong, then the value of the Hubble constant calculated from the early universe might be off. In response, scientists have looked for other ways to measure the expansion rate. One promising method involves gravitational lensing. When a distant object, like a quasar, is lensed by a closer galaxy, the light can take multiple paths to reach us, arriving at slightly different times. By studying the time delay between these light paths and combining that with redshift data, researchers can calculate distances and the Hubble constant independently. These lensing-based values tend to agree more with the supernova measurements than with the early universe predictions. Gravitational waves may also help resolve the tension. When a neutron-star merger is observed in both light and gravitational waves, scientists can calculate how far away it is and compare that to redshift. These standard sirens are still rare, but over time they may provide a third, unbiased way to measure the expansion rate. The tension has sparked deep discussions across cosmology and physics. Some researchers see it as a crack in the foundation of the standard model of cosmology. Others are more cautious, saying we need even better data before jumping to conclusions. But one thing is clear, this is not a small problem. It strikes at the heart of how we understand the universe. The search for answers has also led to new missions and telescopes being designed with this question in mind. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will provide an even more detailed map of the sky and help refine both supernova and lensing measurements. The European Space Agency's Euclid mission will look closely at dark energy and structure in the universe. These missions aim to get to the bottom of the Hubble tension and find out whether it's pointing to a deeper truth about the cosmos. Dark energy, the engine behind acceleration? In the late 1990s, astronomers were measuring the speed at which distant galaxies were moving away from us. The goal was to find out if the universe's expansion was slowing down over time, as most people expected. The idea made sense. Gravity pulls things together, so as the universe expands, its growth should gradually slow. But what they discovered was completely unexpected. Instead of slowing down, the expansion was speeding up. Galaxies weren't just drifting farther apart, they were doing it faster and faster. Something was pushing the universe outward. That something was given a name: dark energy. Dark energy is one of the biggest mysteries in science. It makes up about 70% of everything in the universe, but we don't know what it is. We can't see it, touch it, or detect it directly. All we know is that it's there, because of what it does. Its presence is felt through its effects on space itself. It stretches the universe, making distant galaxies move away from each other at an increasing pace. To understand what dark energy might be, scientists started looking at how it behaves. The first clue came from those distant supernovae. Using them, scientists could figure out how fast the universe was expanding at different times in the past. When they did this, they saw that the expansion was slower billions of years ago than it is now. That meant something had changed. Something started to overpower gravity. That something was dark energy. But what exactly is it? One idea is that dark energy is a property of empty space. This concept goes all the way back to Albert Einstein's cosmological constant. He did it to keep the universe static. He thought the universe neither expanded nor collapsed, and the constant was used to balance out gravity. When the universe's expansion was discovered, he called it his biggest blunder. But decades later, it came back into the picture, because it could explain dark energy. If space has energy built into it, then as the universe grows, more space means more energy. That energy doesn't get diluted like matter does. Instead, it stays constant per unit of space, so as space expands, the overall energy increases. That energy acts like a kind of anti-gravity, pushing everything apart. This is what the cosmological constant explains. It's a simple idea and fits the data fairly well. Still, not everyone is convinced this is the full story. Some scientists think dark energy might not be constant at all. It could be changing over time, or it might behave differently in different parts of the universe. These ideas lead to something called quintessence. That's a name for a type of dark energy that can vary in strength. Unlike the cosmological constant, quintessence would act like a dynamic field, something that fills space and evolves as the universe ages. There are many forms quintessence might take. Some versions weaken over time, others grow stronger. A few might even reverse direction at some point, slowing expansion instead of speeding it up. These different possibilities all have different consequences for the future of the universe. If the force continues to push space apart at an ever-increasing rate, galaxies will get farther and farther away. Eventually, they'll move so fast that their light will never reach us again. The universe will grow colder and darker as stars burn out, and black holes slowly evaporate. This is called the Big Freeze. It's one possible ending, where the universe just keeps expanding forever, becoming emptier and lonelier with time. Another scenario, though less likely based on current data, is the Big Rip. In this case, dark energy grows stronger over time. It doesn't just push galaxies apart, it starts tearing galaxies themselves apart. Then it rips stars from planets, atoms from molecules, and eventually even the particles that make up atoms. This would be the most violent end imaginable, where everything is torn to pieces in the final moments. Then there's the Big Crunch, which would happen if dark energy eventually weakens or turns negative, and gravity takes over again. In this case, the universe could stop expanding and start collapsing. Everything would fall inward until the universe ends in a kind of reverse Big Bang. But current observations don't support this idea, at least for now. To test these theories, scientists need to study dark energy more closely. That means mapping the universe in more detail, measuring how galaxies cluster, and seeing how expansion has changed over time. The more data we get, the better we can understand how dark energy behaves. One important tool for this is baryon acoustic oscillations, or BAO. These are ripples in the distribution of galaxies, caused by sound waves that move through the early universe. By measuring the size of these ripples at different distances, scientists can see how the universe expanded over time. These measurements give clues about how strong dark energy was in the past. It's strange to think that most of the universe is made of something we don't understand at all. Matter, the stuff we see, touch, and measure, makes up less than 5% of everything. Dark matter, which we also haven't fully identified, makes up another 25%. But dark energy is by far the largest part and the least understood. Some scientists even wonder whether dark energy is pointing to a flaw in our basic understanding of physics. Maybe general relativity is incomplete. Perhaps gravity works differently on very large scales. If that's the case, then what we're calling dark energy might be the result of a deeper law we haven't discovered yet. Unveiling cosmic topologies beyond simple geometries. When most people think of the shape of the universe, They imagine something simple: a vast, empty space that either stretches infinitely in all directions or curves around like a giant sphere. In popular discussions, the universe's geometry is often described as either flat, like a sheet of paper, or curved, like the surface of a ball. These ideas are based on the most common models of cosmology, where the universe is thought to behave according to either Euclidean or spherical geometry. However, in recent years, scientists have begun to explore more complex possibilities, ideas that challenge the simple assumption that the universe is either flat or curved in a straightforward manner. Could the universe have a more exotic structure? Could it have strange geometries that twist and fold in ways that are nearly impossible for us to comprehend? The search for the true shape of the universe is leading scientists into the realm of new, less familiar topological models. The geometry of the universe is closely tied to the fabric of space-time, the four-dimensional stage on which everything happens. According to general relativity, the shape of this stage isn't fixed. It can bend and warp depending on the distribution of matter and energy. This warping is what causes the effects we observe, like gravity. The overall geometry of the universe influences how galaxies move, how light travels across vast distances, and even how the universe will evolve in the future. One of the simplest geometries proposed for the universe is the idea of a flat universe, in which space extends infinitely in all directions, with no curvature whatsoever. This is what we find when we look at the most detailed observations of the CMB. According to current measurements, the universe seems to be very close to flat. This means that, on large scales, space behaves as though it follows the rules of ordinary geometry, with parallel lines never meeting, angles adding up to 180 degrees, and so on. However, the flat model only tells part of the story. It assumes that the universe is uniform and unchanging on a large scale, which is generally true for the most part. But some scientists have argued that this simple picture doesn't capture the full complexity of the universe's structure. They believe that the cosmos may have a more intricate and subtle shape. In this view, the universe could have a higher dimensional structure that's difficult to visualize. Just like a two-dimensional surface can be flat, cylindrical, or spherical, the universe could have a multi-dimensional shape that's impossible to describe in our everyday experience. Imagine for a moment a surface with a strange twist, a kind of donut shape. If you were to travel far enough in a straight line in this world, you might eventually return to where you started, but through an unexpected route. This idea is based on the concept of a closed universe, where space itself is finite but has no boundaries. It's not like a box with walls, but more like a loop, where traveling far enough in one direction would bring you back to your starting point. Such a closed, looping universe would not only have a surprising shape, but it would also have far-reaching consequences for how we think about space and time. These topologies are often described in mathematical terms, but imagining them is a different matter entirely. Some researchers have proposed models where the universe has a kind of multi-connected structure. In this type of model, space might contain mysterious holes or wormholes that connect distant regions. The idea is that space itself could be folded in such a way that traveling through one of these wormholes would instantly take you across vast distances. In some versions of this theory, entire galaxies could be linked by these hidden bridges, and the light we see from distant parts of the universe might not be traveling along the path we think it is. Instead, it could be bending and twisting through higher dimensional connections, creating what we call non-trivial topologies. In one of the most radical ideas, some scientists have suggested that our universe could be part of a larger structure, a higher dimensional multiverse. In this view, our universe would be just one of many, each with its own set of physical laws and properties. These universes could be connected through higher dimensional spaces, with our own universe possibly forming a kind of bubble in this greater multiversal structure. These bubbles might interact with each other, and some researchers have even speculated that the collision of two such universes could have created the Big Bang itself. Some topological models suggest that the universe could have a repeating or periodic structure. Imagine that, on the larger scales, space might contain regions that mirror each other, almost like a cosmic version of wallpaper patterns. This could mean that the universe is structured in a way that repeats itself, with each copy of the universe connected to the others by an underlying mathematical rule. This kind of model could explain some of the observed patterns in the universe's structure, including the arrangement of galaxies and galaxy clusters. Another intriguing possibility comes from the idea of a universe that is not only multidimensional, but also fractal in nature. Fractals are patterns that repeat themselves on different scales, like the branches of a tree or the coastline of a jagged mountain. If the universe were fractal, this could mean that the structures we see on large scales, like clusters of galaxies, might have similar patterns on much smaller scales, all the way down to the tiniest subatomic particles. In this case, the universe would be made of repeating, self-similar structures, and this could have profound implications for everything from the distribution of galaxies to the way that space-time itself is structured. Much of the work being done in cosmology today focuses on trying to figure out which of these models best matches what we observe. The complexity of these topological structures means they are hard to test with current technology. But researchers are not giving up, and new tools, better measurements, and more powerful computer simulations are helping to build a clearer picture of the universe's shape. Gravity's role in a multifaceted cosmos. Gravity keeps our feet firmly planted on the ground, pulls objects toward the Earth, and shapes everything from the paths of falling apples to the orbits of planets. While we typically think of gravity through the lens of Newton's laws or Einstein's general relativity, recent discoveries suggest that gravity may be far more complex, especially when applied to the enormous scales of the universe. According to relativity, gravity isn't just a force that pulls objects together, but rather the result of the bending of space-time caused by mass and energy. Massive objects, like the Earth or the Sun, warp the space around them, and this warping is what we experience as gravity. The more massive an object, the greater the curvature of space-time it creates. While general relativity has been confirmed through numerous experiments and observations, its application to large-scale cosmology on the level of galaxies and the entire universe reveals some strange puzzles. For instance, the universe's accelerating expansion challenges traditional expectations about gravity's role in the cosmos. Why does gravity seem to behave differently on cosmological scales? Some possible explanations come from theories that add modifications to general relativity. One such theory is called modified Newtonian dynamics, or MOND, which was first proposed by physicist Mordechai Milgram in the 1980s. MOND suggests that gravity behaves differently at very low accelerations, such as those found in the outer regions of galaxies. According to this theory, the gravitational force doesn't follow the simple inverse square law we are familiar with at large distances. Instead, the force weakens more slowly than expected, allowing galaxies to hold onto their stars and gas clouds more tightly than traditional Newtonian gravity would predict. MOND has had some success in explaining the behavior of galaxies, particularly their rotation curves, the way stars move around the center of the galaxy. But it hasn't been universally accepted. One of the major challenges of MOND is that it doesn't explain everything, particularly when it comes to the behavior of galaxy clusters and the cosmic scale of the universe. Another alternative to general relativity is the idea of a fifth force, or a modification of gravity at larger scales. In this scenario, gravity might not be the only force affecting the universe's evolution. There could be a new force at work, one that influences cosmic expansion and alters our understanding of gravity's role in the cosmos. Some scientists have suggested that such a fifth force could be tied to dark energy. In this view, Gravity is still responsible for the formation of galaxies and stars. But there is an additional force that comes into play at larger scales, one that acts to push the universe apart rather than pull objects together. In some models, gravity could weaken or strengthen depending on the age of the universe or the distribution of matter. If gravity behaves differently in different parts of the universe, this could have profound effects on the evolution of galaxies and the expansion of the cosmos. For instance, if gravity were weaker in the past, galaxies might have formed more slowly, or stars might have burned out at different rates. The exact nature of this time-varying gravity is still up for debate, but it has the potential to radically change our understanding of the universe's history and future. Then there is the concept of quantum gravity, which attempts to combine the principles of quantum mechanics with general relativity. At the smaller scales of reality, such as those involving elementary particles, quantum mechanics governs the behavior of matter and energy. But when we look at the large-scale structure of the universe, the laws of general relativity take over. Quantum gravity seeks to explain how gravity works at these tiny scales, where the effects of both quantum mechanics and gravity are felt simultaneously. In this realm, the force of gravity might not be smooth and continuous, but instead might exhibit quantum fluctuations, tiny, unpredictable changes in the fabric of space-time. These fluctuations could have important implications for our understanding of the early universe, where both gravity and quantum effects would have played a major role in shaping the cosmos. One of the most fascinating ideas in quantum gravity is the concept of loop quantum gravity, which suggests that space-time itself is made up of tiny, discrete units, much like atoms, make up matter. In this theory, gravity is not the smooth, continuous force described by general relativity, but instead is quantized, existing in small, indivisible chunks. This could lead to a completely new way of understanding the structure of the universe, opening up new possibilities for how the cosmos might have evolved and how it could continue to expand. Another area of study is the connection between gravity and dark matter. Dark matter interacts with normal matter through gravity, but it does not emit, absorb, or reflect light, making it incredibly difficult to detect. Its presence is inferred from its gravitational effects on galaxies and galaxy clusters. While scientists have had success modelling dark matter using traditional gravity, it's still unclear exactly what dark matter is. Some theories suggest that dark matter could be made up of particles that interact with gravity in strange ways, possibly involving modifications to our understanding of gravity itself. The relationship between gravity and dark matter is also central to the behaviour of galaxy clusters. These massive groups of galaxies are held together by gravity, and their motion can tell scientists a great deal about the amount of mass present in the universe. The strange way galaxies move in clusters suggests that there is more mass than we can account for with ordinary matter. Some researchers have proposed that this extra mass could be a manifestation of modified gravity, rather than an unknown substance like dark matter. If gravity behaves differently in galaxy clusters, it could help explain many of the anomalies that have puzzled scientists for decades. All of these alternative theories point to one fundamental truth. Gravity, while an essential part of the cosmic story, is far from fully understood. As we continue to refine our understanding of gravity, we may unlock new insights into the forces that govern the universe's expansion and evolution, and perhaps discover a deeper connection between the forces of nature. The realm beyond the observable, our cosmic horizon. In space, there is a boundary that separates what we can observe from what lies beyond our reach. This boundary, known as the cosmic horizon, marks the farthest distance from which light, or any other form of information, can travel to us since the beginning of the universe. It's not a physical wall, but rather a limit to how much of the universe we can see, measure, and study. Beyond this cosmic horizon lies a realm that remains completely out of view, no matter how advanced our telescopes or technologies become. The further away an object is, the faster it moves away from us, a relationship that is described by Hubble's law. As the universe expands, the space between galaxies stretches, carrying light along with it. This stretching of space means that light emitted from objects beyond a certain distance will never be able to reach us, because the space between us and those objects is expanding too rapidly. At some point, the distance is so great that the expansion of space is faster than the speed of light, meaning the light from those distant objects will never have the chance to catch up with us. This creates a limit to our observations. What we can see and study is limited by how far light has had time to travel since the Big Bang. The universe is roughly 13.8 billion years old, and that means that light emitted from objects farther than 46 billion light years away will never reach us, not even in the far future. This region, beyond our observational reach, is what we refer to as the unobservable universe. But what does it mean to have a universe that stretches far beyond our line of sight? To imagine this concept fully, it's helpful to think about the observable universe as a bubble. Inside this bubble, we can see and study everything, from the closest planets and stars to the farthest galaxies and cosmic radiation. However, beyond this bubble lies a vast expanse that remains hidden. These regions are, in a sense, beyond time for us. One important aspect of the cosmic horizon is that it is not fixed in place. It evolves over time as the universe continues to expand. The light we observe today from distant galaxies was emitted millions, even billions of years ago. As the universe expands, the galaxies that were once within our observational reach are now moving beyond the horizon, and new regions of space are constantly coming into view. This means that the observable universe is not a static, unchanging realm, but a dynamic and ever-shifting domain. With each passing moment, the universe gets a little larger in terms of what we can observe, though vast regions remain forever out of our grasp. If there is so much of the universe that we will never see or know about, does that mean it has no bearing on our understanding of the cosmos? Some scientists have argued that the unobservable universe is, for all practical purposes, irrelevant to our current understanding. What exists beyond the cosmic horizon may have no effect on the structure or fate of the observable universe. However, this view is not universally accepted. Many cosmologists believe that even though we cannot observe distant regions directly, the physics governing the universe, such as the laws of gravity, relativity, and quantum mechanics, applies uniformly, no matter how far away an object is. This suggests that the unobservable universe may still follow the same rules, and understanding its properties could help complete our picture of the cosmos. The cosmic horizon also implies that the universe itself is much larger than what we can directly observe. What lies beyond that horizon? Could there be more galaxies, more stars, and perhaps even other regions of the universe that are radically different from what we see? Some theories suggest that the universe may be infinite, extending far beyond the limits of our observable bubble, with galaxies, stars, and even cosmic structures continuing forever. In this view, the universe would never end, and our observable universe would be just a minuscule fraction of a much larger, infinite expanse. In contrast, other theories suggest that the universe may be finite, but still incredibly vast. According to this idea, space might curve back on itself, creating a closed loop. In this scenario, what lies beyond the observable universe would be a continuation of the same structure we see in our own cosmic neighborhood, but we may never be able to access it because of the limitations imposed by the cosmic horizon. Perhaps our universe is just one of many in a multiverse. If this is the case, the unobservable universe could be just one part of a vast, possibly infinite set of parallel universes, each separated by its own cosmic horizon. The notion of the unobservable universe also brings us to a paradox. If we can never observe what lies beyond the cosmic horizon, how can we ever know anything about it? The universe, in this sense, could be forever beyond our knowledge. For some, this limitation might feel frustrating as it represents a boundary that no scientific advancement can cross. No matter how much we learn, there will always be more that we cannot see, no matter how hard we try. However, this doesn't mean that the concept of the unobservable universe is without value. On the contrary, it presents us with an incredible opportunity to stretch the limits of our imagination and theoretical understanding. While we may never be able to directly observe the distant regions of space, scientists continue to look for indirect ways to learn about them. For example, by studying the CMB, scientists can learn about the early stages of the universe, even beyond the current observable limits. They can also look for patterns in the distribution of galaxies that might provide clues about the universe's structure beyond the horizon. As our technologies advance and our theories evolve, we may find new ways to probe the limits of the observable universe and perhaps one day catch a glimpse of the cosmic landscape that lies just beyond the edge of our sight. Entropy Story in a Vast Universe. In the cosmic dance of stars, galaxies and black holes, there is an invisible force quietly dictating the future of everything. Entropy. At its core, entropy is a measure of disorder or randomness. In the most familiar setting, we experience entropy every day, when a tidy room gradually becomes messier with time, even without any intervention. The second law of thermodynamics states that in a closed system, entropy will always increase over time, meaning that systems will naturally evolve toward a state of greater disorder. This law is just as true for the universe as it is for any other system. Over cosmic timescales, stars burn their fuel and reach the end of their life cycles. Galaxies collide and merge, and matter spreads out, increasing the overall entropy of the universe. Entropy provides a thermodynamic arrow of time, a direction that time seems to move. It's a universal trend that everything from the smallest particles to the largest galaxies tends toward a state of higher entropy. This means that in the early universe, when the cosmos was dense, hot, and relatively simple, entropy was lower. As the universe expanded and cooled, complexity and order were created. Stars formed, galaxies clustered together, and life emerged on Earth. But as time progresses, entropy increases, and all these structures will eventually break down and return to a state of greater disorder. When we think about entropy in the context of the universe, the term heat death often comes up. This concept describes a potential end state of the universe where entropy has reached its maximum possible value. In this scenario, all stars would burn out, galaxies would spread apart, and the universe would become a cold, dark, and empty place. The stars that light up the night sky today would be distant memories, their once vibrant energy now dispersed across an ever-expanding cosmos. There would be no life, no movement, and no interactions. Everything would be in a state of maximum disorder, where no further useful energy could be extracted from the system. This idea of the heat death of the universe sounds bleak, but it is one of the most significant predictions that comes from the thermodynamic perspective of entropy. The universe, as it continues to expand, will eventually run out of usable energy. In a universe governed by entropy, it seems that all paths lead toward an end of stasis and stillness, where nothing changes anymore. Yet there are nuances to this thermodynamic fate. While entropy might dictate the eventual disintegration of cosmic structures, the journey towards that ultimate state is not a straight path. The universe is constantly evolving, and different processes contribute to the ever-changing levels of entropy. Some areas of the cosmos experience a local increase in order as stars form and galaxies collide, while other areas see more disorder as black holes devour matter and scatter it across space. In fact, The very existence of stars and galaxies is a result of local decreases in entropy. When matter clumps together under the force of gravity to form a star, it reaches a higher state of order, creating a dense, hot core capable of nuclear fusion. This process is what fuels stars and gives them energy. The formation of stars is a temporary local reduction in entropy. However, this order is never permanent. The star will eventually exhaust its fuel, expanding into a red giant, shedding its outer layers, and leaving behind a dense core in the form of a white dwarf, neutron star, or black hole. The energy produced during a star's life cycle is released into space, increasing the overall entropy of the universe. While they represent one of the most extreme forms of gravitational collapse, black holes also offer a paradox in the study of entropy. According to the laws of thermodynamics, black holes have entropy themselves, which is proportional to their surface area, rather than their volume. This was a revolutionary insight brought about by physicists like Stephen Hawking, who discovered that black holes can radiate energy, a phenomenon known as Hawking radiation. In this way, black holes seem to challenge traditional understandings of entropy, and they have become a central area of research in modern cosmology, particularly when trying to understand the intersection of thermodynamics, quantum mechanics, and gravity. As the universe expands and stars burn out, the amount of usable energy decreases, and the universe will gradually approach a state where no significant processes occur anymore. This heat death scenario may take trillions of years to unfold, but it is the natural consequence of a universe governed by thermodynamic principles. There are some theorists who speculate that in the far future, the universe might experience a big rip instead of a heat death, where the universe continues expanding at an accelerating rate until the very fabric of space itself is torn apart. While this theory is still debated, it presents a different vision of the end of the universe. Understanding entropy is key to understanding not only how the universe came to be, but also where it is heading. Even the most beautiful structures in the universe, like nebulae and star clusters, are merely temporary patterns that will eventually fade into cosmic oblivion. In this sense, entropy is a reminder that the universe is constantly in motion, constantly changing. In the grand scheme, this increase in entropy is what has allowed the universe to evolve in the way it has. It is the very reason that stars have the chance to shine and that life emerged on Earth. Entropy is both a creator and a destroyer. The Big Rip Hypothesis, unraveling space-time. The Big Rip hypothesis describes a scenario in which the universe's expansion accelerates uncontrollably. At first, dark energy was seen as a relatively benign force, causing the universe to expand at a faster rate, but without any obvious consequences. However, the Big Rip hypothesis suggests that dark energy could evolve over time in such a way that it grows stronger and stronger, leading to a runaway effect. In this scenario, galaxies would first be pulled away from each other, as they already are, due to the expansion of the universe. Eventually, as dark energy's strength increases, even the gravitational bonds that hold galaxies together would be overpowered. Entire galaxy clusters, groups of galaxies bound by gravity, would be torn apart. The next stage in the Big Rip scenario would be the disintegration of individual galaxies. Stars, planets, and solar systems would begin to feel the effects of this growing force. The gravitational forces that normally keep stars bound within galaxies would no longer be able to hold them together. Stars would be separated from one another, drifting apart as if they were never part of the same cosmic structure. Planets, once held in the gravitational embrace of their parent stars, would be flung into the void of intergalactic space. In the final moments before the Big Rip, even the fundamental forces that bind atoms together, like the electromagnetic force, which holds electrons in their orbits around nuclei, would be overwhelmed by the accelerating expansion of space. Atoms themselves would begin to disassemble. In this sense, the Big Rip would be the ultimate disintegration of all structure, even down to the most fundamental level. The very fabric of the universe would be stretched and ripped as the expansion reaches its peak. This would not be a simple process of objects moving apart from each other. It would be an unraveling of the very structure that governs reality. The mathematical models that describe this process suggest that space itself would be torn apart at every scale, starting from the largest cosmic structures and working all the way down to the most minuscule subatomic particles. The timing of such an event is still a matter of speculation. Current observation suggests that the expansion of the universe is indeed accelerating, and this has led some scientists to consider the possibility of the Big Rip scenario. However, whether dark energy will continue to increase in strength or whether it will remain constant over time is still unclear. If dark energy continues to grow stronger, the Big Rip could occur within the next few billion years. If it remains relatively stable, however, the universe may continue expanding at a more moderate rate for much longer, with the Big Rip remaining a distant possibility. One of the key pieces of evidence for the Big Rip scenario would be a noticeable increase in the rate of acceleration of the universe's expansion. If the expansion is accelerating in the way the Big Rip predicts, we would see more and more distant galaxies moving away from us at ever-increasing speeds. If future observations continue to show a rapid acceleration of expansion, the idea of the Big Rip would become more plausible. Moreover, by analysing subtle patterns in the CMB, scientists could potentially learn more about how dark energy has behaved in the past and whether it is changing over time. If evidence emerges that dark energy is growing stronger, the likelihood of the Big Rip scenario would increase. It is important to remember that this is just one of several potential outcomes for the fate of the universe. Other models, like the Big Freeze and Big Crunch, propose different endings. The Big Rip, however, stands out because of the extreme and chaotic nature of its scenario. It is an ending that is both terrifying and fascinating. If the universe is destined to end in such a violent and dramatic way, what does that mean for the meaning of life and the place of humanity in the grand scheme of things? Is the universe simply a random series of events that will one day be undone, or is there some deeper purpose behind the forces that drive cosmic evolution? Alternative futures, the Big Bounce scenario. The Big Bounce theory offers a somewhat hopeful alternative to the more catastrophic scenarios for the universe's fate. It suggests that the universe might not have a singular, final ending, but instead undergo a continuous cycle of birth, death, and rebirth. According to this idea, the universe could eventually reach a point where its expansion slows down, halts, and then reverses. Instead of the universe being torn apart, it would collapse in on itself in a big crunch and then bounce back into another expansion, an endless cycle of cosmic rebirth. This cyclical view of the universe's life cycle is rooted in a concept that dates back to the early 20th century. The idea was initially proposed by physicist Alexander Friedmann, who, through his equation, suggested that the universe might not simply be expanding into an empty void, but instead be part of an ongoing cycle of expansion and contraction. These models grew in complexity as scientists learned more about the universe, its geometry, and the forces at play. The more recent Big Bounce theory builds on these early concepts but incorporates modern ideas about dark energy, cosmic inflation, and the shape of the universe. One of the core tenets of the Big Bounce theory is the idea that the universe operates in a kind of loop, where after each expansion phase, a contraction phase follows. This process could be triggered by various factors, such as a collapse of matter or the gradual slowing down of the universe's expansion. Over time, the universe would contract due to gravitational forces, with galaxies, stars, and planets being drawn toward one another. Eventually, everything might collapse into a singularity. The immense heat and pressure of this collapse could trigger another event like the Big Bang, setting off a new period of expansion and allowing the cycle to begin anew. The Big Bounce suggests that the universe, instead of reaching an irreversible end, simply resets itself, continuing on indefinitely. In this sense, the Big Bounce offers a more regenerative view of cosmic destiny, one where the universe never truly dies, but instead evolves in a series of cycles that stretch across infinite time. Current observations suggest that the universe follows the geometric properties of Euclidean space. This is significant because it suggests that the total density of the universe is perfectly balanced between the forces of gravity and the rate of expansion. However, the future evolution of the universe could depend on several variables, such as the amount of dark energy, dark matter, and ordinary matter present, as well as the behavior of space-time itself. If the density of the universe exceeds a critical value, gravitational forces could eventually cause the expansion to slow down, halt, and reverse. This would initiate a contraction phase where galaxies, stars, and other structures are drawn back together. The idea is that the more matter the universe contains, the more likely it is that the universe will eventually collapse back into itself, setting the stage for a new Big Bang and the next expansion phase. However, modern cosmology presents an interesting twist on this idea, especially with the discovery of dark energy, which complicates the Big Bounce theory. If dark energy continues to dominate, it could prevent the universe from contracting at all, leading to the more widely accepted Big Freeze scenario, in which the universe expands forever. However, some variants of the Big Bounce theory propose that the role of dark energy could change over time. In this model, dark energy could eventually weaken or even reverse its influence, allowing gravity to regain control and trigger a contraction. This transition, if it occurs, would then lead to the Big Crunch and ultimately to the next bounce. Quantum effects may play a major role in the behavior of space-time at extremely small scales, such as near the singularity of a collapsed universe. Quantum fluctuations could allow for the smooth transition from contraction to expansion, preventing the kind of catastrophic collapse that might occur in other scenarios. This quantum nature of the universe could make the Big Bounce more likely, as it suggests that the laws of physics could support the transition from one cycle to the next, without the universe getting trapped in a dead-end singularity. One of the most significant obstacles is the lack of direct evidence for a previous bounce. Current cosmological data, including the CMB, suggests that the universe began in a singularity we call the Big Bang. But there is no clear evidence that the universe underwent any earlier cycles of expansion and contraction. In fact, the idea of a cyclical universe is in direct contrast to the more widely accepted notion of a single beginning, with the Big Bang marking the origin of everything. To further complicate matters, there is the question of how entropy fits into the Big Bounce theory. In the current universe, entropy has been steadily increasing, and according to the second law of thermodynamics, the overall disorder in the universe must continue to rise over time. If the universe undergoes repeated cycles of contraction and expansion, the question arises as to how entropy could reset after each bounce. Some proponents of the Big Bounce theory suggest that entropy could be partially reset with each cycle, while others propose more complex mechanisms that allow the universe to continue cycling without accumulating too much disorder. How this would work remains a mystery, as the mechanisms behind entropy in a cyclic universe are not fully understood. The Big Bounce theory often runs into difficulties when trying to explain the detailed structure of the universe, such as the formation of galaxies, stars, and other cosmic structures. In a universe that goes through repeated expansions and contractions, the conditions for star formation and galaxy evolution may not follow the patterns we see today. The question of how the universe could maintain its structure through an infinite series of bounces remains a topic of debate and research. Some models suggest that each bounce might create a slightly different universe, with new structures forming each time, while others propose that the universe's structure is preserved in some way through each cycle. Whether or not the Big Bounce will prove to be the ultimate fate of the universe is still an open question, but its cyclical vision of cosmic destiny provides an intriguing alternative to more traditional views of the universe's ending. Cyclic models of the universe. New insights in old ideas. The concept of a cyclic universe is one of the oldest ideas in cosmology. For thousands of years, philosophers and scientists have wondered if the universe's existence is defined by a single birth and death, or whether it undergoes repeated cycles of creation and destruction. While the idea of a cyclic cosmos has ancient roots in philosophies and early scientific models, modern cosmology has breathed new life into these old ideas, using new data and theoretical frameworks to explore how the universe might function as a series of recurring cycles, rather than a one-time event. In Hindu cosmology, the universe is thought to undergo an endless cycle of creation, preservation, and destruction, a concept that inspired similar ideas in Western thought. In ancient Greek philosophy, thinkers like Plato and Aristotle pondered whether the universe had always existed in a constant, unchanging state, or if it had experienced cycles of rebirth. However, it was not until the 20th century, with the advent of modern physics and the understanding of cosmological principles, that the cyclic universe model began to gain more scientific attention. Modern cyclic models, while building on older ideas, take into account the growing body of cosmological data, particularly from the discovery of dark energy, which is driving the accelerated expansion of the universe. One prominent theory is the ekpyrotic model, or cyclic model of the universe, proposed by physicists Paul Steinhardt and Neil Turok. This model, introduced in the early 2000s, suggests that the universe's cycles could be the result of collisions between higher dimensional branes or multi-dimensional objects in string theory. According to this idea, our universe exists on one of these branes, and the cycle of cosmic expansion and contraction is driven by the interactions of these branes. In this model, the universe does not start from a singularity in the traditional sense, but instead undergoes periodic bounces, driven by these collisions. Rather than a universe collapsing and then exploding again in a new Big Bang, the ekpyrotic model suggests that each cycle is triggered by the collision of branes, which causes a dramatic release of energy that initiates a new cycle of expansion. This model has received attention due to its ability to address some of the challenges posed by traditional cyclic models, including the problem of entropy accumulation in each cycle, which would otherwise make the universe progressively more disordered with each iteration. Another fascinating idea is the conformal cyclic cosmology, or CCC, proposed by physicist Roger Penrose. The CCC model builds on the idea of a cyclic universe, but suggests that each cycle is not separated by a dramatic big crunch, but instead fades into an infinite future. According to Penrose, as the universe expands, matter and energy become more spread out, and eventually reach a state of perfect smoothness, where the distinction between the past and future disappears. In this scenario, the current universe's far future, dominated by dark energy, and a smooth, uniform universe, would seamlessly transition into the beginning of the next cycle, starting with a new Big Bang-like event. Penrose's model proposes that each cycle could last for a vastly long period, and each successive cycle is effectively a new beginning for the universe, with the conditions of the previous cycle leaving a kind of memory imprint. While CCC is an elegant theoretical model, it too faces challenges, most notably the need for further evidence to support the idea that entropy in the universe could be reset as the universe transitions between cycles. Nonetheless, it provides a fascinating framework for thinking about the universe's long-term evolution, suggesting that the universe's history may be composed of many epochs, each one more mysterious than the last. As modern cosmology continues to gather data through powerful telescopes and experiments, It may yet uncover more evidence supporting the idea that the universe is not a one-time creation, but a continuous process of birth, death, and rebirth. Whether or not cyclic models become a central feature of cosmological theory remains to be seen, but they certainly offer an exciting alternative to the more conventional theories about the universe's past and future. Higher dimensions and brain cosmology, multiverse perspectives. At first glance, the thought of higher dimensions beyond our familiar three-dimensional space can seem almost impossible to grasp. After all, we live in a world where objects and events are typically confined to the three dimensions we interact with daily: length, width, and height. But in the early 20th century, Albert Einstein's relativity introduced a radically new way of looking at the universe, revealing that time and space are interconnected, forming a four-dimensional fabric known as space-time. Since then, the idea of extra dimensions has been pursued by physicists, with increasingly sophisticated theories suggesting that more dimensions could exist beyond the four we observe. The theory of higher dimensions gained significant attention with string theory, a framework that attempts to reconcile quantum mechanics and general relativity. According to string theory, the fundamental particles that make up matter are not point-like, as previously believed, but are instead tiny, vibrating strings. These strings vibrate in multiple dimensions, potentially beyond the familiar four. In the simplest versions of string theory, there are 10 dimensions, 9 of space and 1 of time, though some variations propose as many as 11 or 12 dimensions. But if these extra dimensions exist, why can't we perceive them? The answer, according to string theory and related models, lies in the way the extra dimensions are structured. Instead of extending through all of space, these additional dimensions may be curled up or compactified in such a way that they are too small to be noticed at the scale of human observation. Imagine a garden hose. From a distance, it appears to be a one-dimensional line, but if you look closely, you see it has a circular cross-section. This would be analogous to the extra dimensions being curled up into tiny, hidden spaces. These extra dimensions may not be physically noticeable in everyday life, but they could play a crucial role in the fundamental workings of the universe. It is here that the concept of brain cosmology comes into play. In this framework, our universe is thought of as a brain embedded in a higher dimensional space. A brain is short for membrane, a term used to describe a multidimensional object that exists within a higher dimensional space. In simple terms, a brain is a three-dimensional surface, in the case of our universe, that is embedded in a higher dimensional space, which may have additional dimensions beyond our perception. In this picture, our universe could be a three-dimensional brain, floating in a higher dimensional space with more than the three familiar dimensions. In brain cosmology, our universe could be one of many parallel universes, all coexisting in the higher dimensional space. These universes are often thought to be separate from one another, with their own unique sets of physical conditions and realities. However, they may be able to interact with each other under certain circumstances. In the brain cosmology model, the Big Bang may not be a one-time event, but the result of an interaction between two different brains in a higher dimensional space. This idea suggests that our universe may not have had a single, unique beginning, but could be the product of ongoing processes that involve multiple, interacting universes. In brain cosmology, the properties of this higher dimensional space could influence the behavior of the universe we observe. The force of gravity may be much weaker than the other forces in nature because it spreads out over the higher dimensional space, rather than being confined to our three-dimensional brain. This could explain some of the puzzling features of gravity, such as why it seems so weak compared to the electromagnetic, strong nuclear, and weak nuclear forces. If brain cosmology is correct, it would suggest that the universe we experience is just a small part of a much larger, more complex reality. This could open up new avenues of exploration for physicists, who may one day be able to test the existence of other universes or higher dimensional spaces. Certain properties of our universe, such as the distribution of galaxies or the behavior of dark matter, might be influenced by the presence of other brains in the higher dimensional space. These ideas are still speculative, but they provide an exciting new direction for cosmological research. While we are far from fully understanding the implications of these theories, they offer a fascinating glimpse into the possibility that our universe is just one small piece of a much larger, more mysterious cosmic puzzle, dark matter's hidden hand in shaping cosmic destiny. Scientists first began to suspect the existence of dark matter in the 1930s when Swiss astronomer Fritz Zwicky made a startling observation while studying the Coma galaxy cluster. Zwicky noticed that the galaxies in the cluster were moving far too fast for the amount of visible matter present. The gravity from the visible matter simply wasn't enough to hold the galaxies together. There must, he reasoned, be some unseen mass, something invisible, but with a gravitational pull that was keeping the cluster intact. Since Zwicky's early work, scientists have continued to uncover more evidence of dark matter's presence. In fact, it is now estimated that around 85% of the total matter in the universe is made up of dark matter, with the remaining 15% being the regular matter we are familiar with. The presence of dark matter helps explain the distribution of galaxies throughout the universe. Large-scale surveys of the universe have revealed a vast, interconnected web of galaxies, an intricate cosmic network of filaments and voids. These filaments, which connect galaxies into vast cosmic structures, are thought to be shaped by the gravitational influence of dark matter. As dark matter clumps together in certain regions of the universe, it creates gravitational wells that draw in normal matter, causing galaxies to form and align along these filaments. This cosmic web is a direct consequence of dark matter's role in shaping the universe on the larger scales. But dark matter doesn't just influence the formation and behavior of galaxies. It also has a hand in shaping the evolution of the entire cosmos. In the early stages of the universe, dark matter's gravitational pull helped slow down the expansion of the cosmos. Without it, the universe would have expanded much more rapidly in its infancy, and the formation of galaxies and other cosmic structures may not have been possible. As galaxies evolve, they interact with one another through gravitational forces. These interactions, whether through mergers, tidal forces, or other forms of gravitational perturbation, are fundamental to the ongoing process of galaxy formation. But dark matter plays a crucial role in stabilizing these interactions. Without dark matter, galaxies would be more prone to violent disintegration, and the large-scale structure of the universe would be much less stable. Scientists have yet to detect dark matter directly, and its true nature remains a subject of intense investigation. While the leading theories suggest that dark matter is made up of weakly interacting massive particles, or WIMPs, other possibilities such as axions or sterile neutrinos have also been proposed. There are even more speculative ideas, such as the possibility that dark matter is a manifestation of extra dimensions. Experiments such as the Large Hadron Collider, the Dark Energy Survey, and the search for dark matter in underground laboratories are just a few of the efforts underway to better understand this invisible force. Although dark matter remains hidden from view, the knowledge that it is out there, shaping the very fabric of the cosmos, drives cosmologists to push further into the unknown. The universe's subtle symphony, acoustic oscillations, and their legacy. When the universe was still young, it was a hot, dense sea of particles. Protons, neutrons, and electrons floated freely in an ionized state, and the temperature was so high that atoms couldn't form. In this environment, radiation was constantly scattering off free electrons, creating a fog that kept light from traveling freely. However, as the universe cooled, it began to transition, and atoms formed. At this moment, known as recombination, the universe became transparent, allowing light to travel across space for the first time. This light, which we now observe as the CMB radiation, carries a snapshot of the universe at that moment. The CMB is not just a simple image, it's a detailed record of the tiny temperature fluctuations that existed at the time. These fluctuations, which are minuscule, about 1 part in 100,000, tell us a great deal about the conditions that existed in the early universe. They represent the seeds of the structures that would later grow into the galaxies, stars, and clusters we see today. But within these temperature fluctuations, there's something else, something even deeper. The imprint of acoustic oscillations, or the sound waves of the early universe. In the dense plasma of the early universe, sound waves propagated through the matter, creating pressure variations that oscillated like the ripples of a drumhead. These oscillations were caused by the interplay between radiation and matter. The radiation, photons, exerted pressure on the gas, pushing it outward, while the gravity of the matter was pulling it inward. This push-pull dynamic created standing waves, like the ones you might find in a musical instrument. The density of the universe at that moment was influenced by these oscillations, with some regions of the universe being slightly more compressed and others less so. As the universe expanded and cooled, these sound waves became frozen in place. When the universe became transparent at recombination, the waves were frozen in the CMB, leaving behind a snapshot of their oscillating pattern. These patterns can still be observed today in the form of tiny variations in temperature across the CMB. These temperature fluctuations are organized, and their arrangement can be studied to understand the nature of the universe at the time. These oscillations tell us a lot about the universe's composition and structure. By studying the CMB, scientists can determine key properties of the universe. The peaks and troughs of the sound waves correspond to the density of the universe at different scales. The largest oscillations, or the first peak, represent the largest structures, regions that were denser than their surroundings, where galaxies and clusters would later form. Smaller peaks represent finer structures, helping to map the universe's evolution. One of the most important discoveries from studying these acoustic oscillations was the determination of the age and expansion rate of the universe. The first peak in the oscillation pattern is particularly useful for this. It tells us about the scale of the universe and how much matter it contained at the time of recombination. The spacing between these peaks can tell us how fast the universe was expanding and how the expansion rate has changed over time. The legacy of these sound waves in the early universe is profound. The imprints they left in the CMB serve as a powerful tool for cosmologists today. By studying them, scientists can test models of the universe's evolution. The role of neutrinos in a dynamic cosmos. Neutrinos are elementary particles, meaning they are not made up of smaller components like protons or neutrons. They belong to a group of particles known as leptons, and they have some fascinating properties. First and foremost, they have an incredibly small mass, almost zero by comparison to particles like protons and electrons. They are also electrically neutral, meaning they do not carry a charge, which further reduces their interaction with other particles. In fact, neutrinos interact with matter so weakly that billions of them pass through us every second without us even noticing. Despite this, neutrinos can have a profound effect on the cosmos, shaping cosmic events at a very fundamental level. Every star, from our Sun to the most massive supergiants, produces an immense number of neutrinos during their nuclear fusion processes. In the Sun, for example, hydrogen atoms are fused together to form helium in a process that releases vast amounts of energy, light, and neutrinos. These neutrinos escape the core of the Sun almost immediately after they are produced and travel through space. Scientists have managed to measure the number of neutrinos that reach Earth, providing valuable insights into the inner workings of our star. The Sun's neutrinos are an important tool in understanding the processes that govern stellar life cycles and nuclear fusion. When a star exhausts its nuclear fuel, the core collapses under its own gravity, triggering a powerful explosion that releases an enormous amount of energy. During this explosion, neutrinos are produced in staggering quantities, and they carry away much of the energy from the core. In fact, supernovae emit far more energy in the form of neutrinos than they do in visible light. By studying the neutrinos emitted by a supernova, scientists can learn more about the processes taking place inside a dying star and gain a deeper understanding of the birth of elements in the universe. One of the most significant impacts neutrinos have on cosmic evolution is in the formation and behavior of galaxies. As the universe began to cool after the Big Bang, matter began to clump together, forming the first galaxies. Neutrinos, though interacting weakly with matter, had an important part to play in this process. In the early universe, neutrinos were produced in huge quantities during the Big Bang, and their distribution helped shape the large-scale structure of the universe. While normal matter began to clump together to form galaxies and stars, neutrinos remained more spread out, traveling freely through space. Their weak interaction with normal matter allowed them to escape from gravitational wells much more easily, which meant they didn't get trapped in the dense regions where galaxies were forming. Instead, neutrinos created a cosmic neutrino background, a sea of particles that permeated the entire universe. This background of neutrinos acted as a kind of pressure that slowed down the formation of dense cosmic structures. Without the influence of neutrinos, the universe might have formed large structures more quickly, altering the evolution of galaxies and clusters. Much like the CMB, the cosmic neutrino background provides a kind of echo of the early universe, offering scientists a glimpse into the conditions that existed just moments after the birth of the cosmos. Though neutrinos are far more difficult to detect than the CMB, they can still provide important clues about the early history of the universe and the processes that took place during the first moments of cosmic evolution. As the universe continues to expand, stars will burn out and galaxies will drift farther apart. During this process, neutrinos will continue to play a role in carrying energy away from various cosmic processes. In fact, as the universe cools and decays, neutrinos will become one of the dominant forms of energy in the cosmos. The contribution of neutrinos to the overall energy budget of the universe will become increasingly significant in this distant future. Over the past few decades, scientists have made significant progress in studying neutrinos. Detectors located deep underground or beneath the ocean have been developed to shield them from other cosmic rays and to detect the faint interactions of neutrinos with matter. These detectors have provided valuable insights into the properties of neutrinos, such as their tiny mass and the fact that they can change flavors as they travel through space. Understanding neutrinos could help scientists answer some of the most fundamental questions in cosmology, such as the behavior of cosmic inflation and the fate of the universe itself. Topology transitions, when the universe changes its shape. As the universe continues its expansion, it is possible that space itself may undergo sudden, dramatic shifts in its shape or structure. These transitions in the universe's topology could lead to scenarios where space itself changes its connectivity or even its dimensional properties, fundamentally altering how we experience and interact with the cosmos. A topology transition, in simple terms, would be a shift in the way space is organized on a grand scale. Imagine a situation where the universe, which seems to expand outwardly and stretch over vast distances, might suddenly fold or unfold in some way. This could be similar to how a sheet of paper can be folded into different shapes, changing the connectivity of the surface in ways that are not immediately obvious but fundamentally alter the nature of space itself. To begin understanding these transitions, it's helpful to imagine the universe as a living entity, one whose shape and structure are not fixed, but may evolve over time. This view presents the possibility that the universe's very fabric could change from one state to another, resulting in a completely new form of space. Imagine a universe that, instead of being infinite or finite in a simple sense, begins to transition between such topologies, shifting from something like a flat plane to a more complex structure that twists, folds, or perhaps even has multiple dimensions that become more apparent with time. One such potential transition in the universe's topology involves the concept of cosmic holes. There could be instances when large areas of the universe simply collapse or get punctured, creating regions of space where the normal rules of physics no longer apply. These punctured areas could represent transitions where space itself is no longer continuous, creating holes or regions where the concept of distance, time, and matter could behave in completely unfamiliar ways. Another form of transition might involve the curvature of space-time. As the universe continues to expand, it is possible that this expansion could cause a sudden shift in the curvature of space-time, transforming its geometry. For example, it could go from a flat shape to something more highly curved, where regions of the universe could fold over on themselves. This kind of topological transition would drastically alter the way galaxies, stars, and planets interact with each other. What once appeared to be a vast, expanding universe might shift into a completely new form, where the laws of gravity, light, and time behave very differently than we are accustomed to. If space were to undergo a dramatic topological shift, it could create portals or bridges to other parts of the multiverse, effectively linking different universes together in ways that may one day be observable, if the laws of physics allow for such interactions. These topological transitions might also explain some of the strange phenomena we observe in the universe today. For example, the fact that galaxies seem to be clustered in large-scale structures known as superclusters might be the result of subtle shifts in the topology of space-time. Perhaps these large structures represent remnants of past topological changes, where space itself was once configured differently. Similarly, the apparent flatness of the universe might also be a result of a topological transition in the distant past. At some point, the universe could have undergone a shift that flattened it out, creating the uniformity we observe today. Additionally, there could be moments in the future when such transitions become more noticeable. As the universe continues to expand, we may discover that space itself is not as rigid and unchanging as we once believed. A topological shift might be triggered by an event like the eventual death of a star, or the merger of two massive black holes, or even by a phase transition in the nature of dark energy. In cosmology, we are constantly attempting to map the universe and understand its structure. But what if the structure itself could change? Are we living in a universe that is alive in the sense that it can change and evolve? Or is it something that is bound to a predetermined fate? Emerging anomalies in cosmic microwave background data. For decades, scientists have studied the CMB with great attention, using it as a cosmic map to trace the evolution of the universe and to test the predictions of various cosmological models. But astronomers have also noticed a number of subtle irregularities in the data, anomalies that don't quite match up with our established theories. The primary feature of the CMB that scientists have long focused on is its near-perfect uniformity. This smooth background radiation with slight temperature fluctuations suggests that the universe, after the Big Bang, rapidly expanded and cooled in a very uniform manner. The tiny fluctuations seen in the CMB are the seeds of the galaxies and large-scale structures that we observe today. But despite this general uniformity, certain patterns in the data have emerged that are difficult to explain using current models of cosmology. These irregularities, often referred to as anomalies, may point to new physics or aspects of the universe that we have yet to fully understand. One of the most talked about anomalies in the CMB data is known as the cold spot. This feature, a large, unusually cold region in the CMB, was first discovered by the Wilkinson Microwave Anisotropy Probe and later confirmed by the Planck satellite. The cold spot is about 5 times larger than expected for a typical fluctuation in the early universe, and its exact cause remains a mystery. Some scientists have suggested that the cold spot could be a sign of a large-scale cosmic structure, like a supervoid, a vast region of space that contains very few galaxies and almost no matter. This supervoid could be influencing the CMB in such a way that it causes the temperature in that region to drop significantly. However, other researchers have proposed that the cold spot might be evidence of something more exotic, such as interactions with other universes. Another notable anomaly that has generated significant discussion is the axis of evil. This is a term used to describe an unusual alignment seen in the large-scale patterns of the CMB. The axis of evil refers to a seemingly coordinated alignment of temperature fluctuations in the CMB that align in a specific direction in the sky. According to the standard cosmological model, these fluctuations should be randomly distributed across the sky, with no preferred direction. However, the axis of evil suggests that there is some underlying preferred direction to the CMB, an irregularity that can't easily be explained. Some theorists have speculated that this anomaly might be caused by some kind of systematic error in the measurements or by contamination from foreground sources of radiation, such as our galaxy's own radiation. Yet others have proposed the possibility that this alignment could reflect the influence of cosmic processes or forces that we haven't yet discovered. The power spectrum of the CMB, which measures the distribution of temperature fluctuations across different angular scales, appears to show a curious dip at larger angular scales. This dip is not predicted by the standard cosmological model, which suggests that fluctuation should be evenly distributed across all scales. The cause of this deviation remains uncertain, though some researchers have speculated that it could be related to cosmic inflation. According to this idea, the inflationary period may have produced a signature in the CMB that we are only just beginning to understand. Another possibility is that these discrepancies might point to the need for a revision in our models of dark matter or dark energy. These anomalies in the CMB data challenge some of the basic assumptions of the lambda-CDM model. Could they be pointing to a deeper, more complex reality? One possibility is that these anomalies might be the result of interactions between the observable universe and a multiverse. Though this idea remains highly speculative, it presents a fascinating possibility that goes beyond the confines of traditional cosmology. If the anomalies in the CMB are related to dark energy, they could provide us with vital clues about its true nature and how it might be shaping the fate of the cosmos. Finally, some researchers have proposed that the anomalies in the CMB data could be a sign that the standard model of cosmology needs to be revised. This could involve tweaking existing theories or introducing new ideas altogether, such as modifying general relativity or exploring alternative gravity theories. Cosmological simulations, peering into the future of expansion. While direct observation remains one of the most reliable tools for studying the cosmos, scientists have turned increasingly to computational simulations to explore the universe in ways that would be otherwise impossible. These simulations, or virtual experiments, allow researchers to test ideas and theories about cosmic expansion, structure formation, and other phenomena, without needing to wait for new data from telescopes or space missions. Essentially, they serve as a sandbox for cosmologists, providing a way to model the universe's evolution across vast timescales. The fundamental goal of cosmological simulations is to replicate the behavior of the universe, starting from the Big Bang, and progressing through time, all the way to the present day and beyond. These simulations rely on the laws of physics, particularly those governing gravity, thermodynamics, and the behavior of particles, to simulate how the universe's various components, like galaxies, clusters of galaxies, and even the vast stretches of empty space, interact with one another. By inputting the known properties of the universe, such as the distribution of matter, the nature of dark energy, and the influence of gravity, scientists can create virtual universes that evolve just like our own. These simulated universes provide us with the ability to explore different cosmic scenarios and investigate what might happen under different conditions. One of the most important aspects of these simulations is that they allow scientists to test different models of cosmic expansion. Cosmologists use simulations to model how the universe might behave under different assumptions about dark energy. By tweaking various parameters, like the amount of dark energy present or the rate at which it grows over time, scientists can simulate different what-if scenarios and observe the outcomes. One popular method of cosmological simulation is called N-body simulation, which focuses on simulating the gravitational interactions between large numbers of particles, or bodies, within the universe. These simulations are particularly useful for studying the formation of structures like galaxies, clusters, and superclusters. N-body simulations allow researchers to simulate the growth of these structures from the initial tiny fluctuations present in the early universe, gradually showing how gravity pulls matter together to form larger and more complex structures. The results of these simulations can then be compared to actual observations, helping to test theories about how structures like galaxies and clusters of galaxies formed and evolved. Hydrodynamical simulations account for the interactions between gas particles in addition to gravitational forces. These simulations are crucial for studying the role of gas in galaxy formation, star formation, and even the behavior of supermassive black holes. By simulating the way gas cools and condenses to form stars and galaxies, cosmologists can explore how the early universe transitioned from a hot, diffuse state to the richly structured cosmos we see today, and how it will further evolve into the future. To test ideas about the universe's large-scale geometry, cosmologists use simulations to explore how different geometric configurations affect the expansion of the universe. By comparing these simulations with observational data, researchers can determine which models best match the universe we observe. As the universe expands, galaxies, stars, and clusters of galaxies are constantly evolving. These structures can merge, collide, and change shape over billions of years, and simulations allow scientists to explore how these processes unfold. For instance, one major goal of modern cosmology is to understand how galaxy clusters form and grow over time. Simulations that incorporate both dark matter and ordinary matter have provided valuable insights into the way these clusters evolve and how their growth might be influenced by cosmic acceleration. They can also help scientists understand the role of dark energy in shaping the fate of these structures in the far future. Cosmologists are particularly interested in exploring what will happen to the universe as it continues to expand. Will the acceleration continue indefinitely, causing galaxies to drift farther and farther apart? Will the expansion eventually slow down and reverse, causing the universe to collapse in on itself? Or could the universe settle into a steady state, with expansion proceeding at a constant rate? By running simulations of the universe's expansion under various assumptions about the nature of dark energy and other components, scientists can test these possibilities and get a clearer picture of the universe's long-term trajectory. One of the challenges of cosmological simulations is the sheer amount of computational power required. Modelling the universe, even on a small scale, is an incredibly complex task. The universe contains a staggering number of particles, and the interactions between them can't be reduced to simple formulas. To accurately simulate the evolution of cosmic structures, scientists use some of the most powerful supercomputers in the world. These supercomputers can run simulations involving billions of particles, taking into account the laws of physics and the forces acting on them. These simulations can take days, weeks, or even months to run, depending on their complexity, and the results are often visualized as stunning three-dimensional models of the universe in motion. By simulating the universe's past, present, and future, cosmologists are able to make predictions that can guide future observations and experiments. In this way, simulations play an essential role in extending our observational capabilities, providing us with a tool to peer deeper into the universe's history and to anticipate its future. Non-standard cosmologies, testing the boundaries of theory. While the standard model of cosmology, the lambda-c/dm model, has been remarkably successful in explaining much of what we observe about the universe, it's important to remember that scientific understanding is always evolving. Over the years, some researchers have proposed non-standard cosmological models that challenge aspects of the prevailing framework, offering alternative perspectives that question our assumptions about the nature of the universe. These non-standard cosmologies are important because they not only push the boundaries of what we know, but also help refine our understanding by forcing us to test our theories in new and creative ways. One such alternative model is MOND, which proposes that the behavior of gravity at large distances might be different than at smaller scales. While MOND has had some success in explaining certain observations, it still faces challenges, particularly in explaining phenomena at larger cosmological scales, such as the CMB or the clustering of galaxies on the larger scales. Other non-standard cosmologies extend this idea by suggesting that the entire framework of general relativity could be altered. For instance, some theories, sometimes referred to as variable gravity models, are built on the idea that the gravitational constant, g, could have evolved during cosmic history, which would influence the rate of expansion of the universe and the behavior of large-scale structures. Some variants of these theories suggest that gravity might have been weaker in the distant past, explaining some aspects of cosmic evolution that are difficult to reconcile with standard models. Another significant area of alternative cosmology challenges the very notion of the Big Bang. One such theory is the steady-state model, which posits that the universe has always existed in a similar state, and that new matter is continually created to fill the gaps left by the expansion of the universe. In this model, the universe does not have a singular origin, but has instead always existed in a steady state of continuous expansion and creation of matter. Though the steady-state model has by now been largely abandoned, it still provides a point of comparison for more modern, non-standard models. More contemporary alternatives to the Big Bang are the cyclical model or the multiverse model of the universe. In addition to these well-known alternatives, there are other theories that seek to explain the universe in radically different ways. For example, some models suggest that the universe might be fundamentally non-local, meaning that events in one region of space-time could influence other regions instantly, regardless of the distance between them. This idea challenges the principle of locality, which is a cornerstone of modern physics and proposes a radically different way of understanding the fabric of reality. Similarly, some theories suggest that space-time might be emergent, meaning that it arises from more fundamental entities or principles that we do not yet fully understand. While lambda-CDM is firmly grounded in observational evidence, many of the non-standard models are still speculative, and their predictions are difficult to test directly. This makes them inherently more challenging, but also more exciting for researchers who are eager to explore the unknown boundaries of cosmology. They help to refine our understanding by presenting new ways of thinking about the universe. By challenging conventional wisdom, they force cosmologists to reconsider their assumptions, rigorously test their models, and consider new possibilities that could shape our understanding of the cosmos. Energy conditions and the fate of the cosmos. Energy conditions are theoretical requirements that govern the behavior of matter and energy in the universe, helping to explain things like how space-time curves, how gravity acts on matter, and even the ultimate fate of the cosmos. These energy conditions are vital pieces in the puzzle of cosmology, as they dictate what is possible within the universe's boundaries and what might lie ahead in its future. They act as guides for understanding the fundamental laws that rule the cosmos and offer insights into how these laws might shape the universe's endgame. Energy conditions are rooted in general relativity and are usually applied to models of space-time to ensure that they remain physically plausible. In essence, they help define the limits of what we can expect the universe to do, based on how energy and matter behave within it. Though abstract in nature, energy conditions provide the foundation for understanding some of the most profound mysteries of the cosmos, including the universe's ultimate fate. One of the most important energy conditions is the null energy condition, or NEC, which dictates that no object can travel faster than the speed of light. This is not just a rule for particles and objects, but applies to the fabric of space itself. It implies that nothing can escape from the gravitational well of a black hole or other regions of extreme gravitational force faster than the speed of light. The NEC also has profound implications for the structure of space-time, particularly when it comes to phenomena like wormholes, time travel, and the overall expansion of the universe. Another crucial energy condition is the weak energy condition, or WEC. The WEC states that in a given region of space-time, the energy density of any object must be positive. In simple terms, this means that you cannot have negative energy, something that could lead to bizarre effects like time loops or a collapsing universe. The WEC helps ensure that matter behaves in predictable ways that are consistent with the observable universe. It essentially places limits on the kinds of exotic phenomena that can occur in space-time, such as negative mass particles or unusual exotic matter. While the weak energy condition doesn't prevent unusual events from happening, it limits the kinds of theoretical scenarios that are physically possible. The dominant energy condition, or DEC, places limits on the energy density of an object, specifying that it must be non-negative and must be distributed in such a way that energy flows into the future, not backward in time. This energy condition is crucial when considering the dynamics of cosmic events like the collapse of stars, the formation of black holes, and even the structure of the early universe. The DEC is critical in ensuring that energy behaves in ways that are consistent with both our current understanding of physics and with the observable universe. It prevents situations where energy would behave in impossible ways, such as violating causality or producing paradoxes that would make the universe's evolution unpredictable. Beyond these basic conditions, there are more advanced energy conditions that are part of our understanding of the universe's fate. These conditions provide the framework for more speculative scenarios about the universe's future, including its ultimate end. The strong energy condition, or SEC, for example, deals with the distribution of energy on large scales and has significant implications for the structure of the universe itself. The SEC plays a key role in models of cosmic inflation, and it also governs the behavior of gravity on large scales, helping to shape the cosmic landscape of galaxy clusters and superclusters. By limiting the kinds of gravitational behavior that can occur, the SEC plays an essential role in understanding the long-term evolution of the universe. Together, these energy conditions shape the laws that dictate the universe's fate. Depending on how they are satisfied or violated, they provide insights into the possible futures of the cosmos. For example, if the DEC holds true, then the future of the universe will be shaped by the kind of matter and energy that we observe today. matter and energy will continue to behave according to the laws of physics as we know them, with galaxies continuing to move apart due to the expansion of space. On the other hand, if some of these energy conditions are violated, it opens up the possibility for more exotic and extreme scenarios. One such scenario is the Big Crunch, which is in direct contrast to the current expectation that the universe will continue to expand indefinitely. If certain energy conditions are violated, such as the WEC or the DEC, the collapse of the universe could be more extreme, potentially leading to the formation of a singularity. Energy conditions help us better understand the stability of the universe on different scales. For instance, the WEC ensures that our current understanding of black holes remains valid, preventing the kinds of paradoxical scenarios in which black holes would behave in unexpected or non-physical ways. Similarly, the DEC limits the types of particles and exotic matter that can exist, ensuring that matter behaves predictably at both small and large scales. But the real intrigue lies in the potential violation of these conditions, opening doors to new physics that we have yet to fully explore. A violation of these conditions could signal the presence of new forms of energy or matter, possibly even undiscovered particles or fields that influence cosmic evolution in ways we don't yet understand. It could also suggest a deeper connection between space-time and the forces that govern the cosmos, offering tantalizing possibilities for breakthroughs in both cosmology and fundamental physics. The ultimate fate of the cosmos is still a mystery, but by studying energy conditions, we are piecing together the puzzle of how the universe might come to an end and what may come after. Observational frontiers. Current observations, while groundbreaking, only scratch the surface of what is out there. The mysteries of cosmic acceleration, dark matter, dark energy, and even the fundamental properties of space-time itself continue to elude us. However, the future holds incredible promise. With the advancement of technology and the development of more powerful observatories, upcoming scientific missions could provide the tools we need to solve some of these great cosmic puzzles. One such project is the Square Kilometre Array, or SKA, which is set to become the world's largest radio telescope when it is completed. This ambitious array of radio antennas, spread across South Africa and Australia, will allow scientists to observe the universe in the radio frequency spectrum. The SKA will provide detailed data about the formation and evolution of galaxies, star systems, and black holes, as well as give insight into cosmic phenomena such as pulsars, supernovae, and gamma-ray bursts. One of the most exciting aspects of the SKA is its potential to investigate dark matter. The SKA will be capable of conducting detailed surveys of the universe's large-scale structure, mapping out the distribution of galaxies and galaxy clusters. By studying the way dark matter influences the movement of galaxies, the SKA could provide vital clues about this elusive substance. The European Space Agency's Euclid mission is another promising project. Launched in 2023, Euclid is designed to investigate the geometry of the dark universe. By mapping the shapes and distributions of galaxies across vast portions of the sky, Euclid will provide insights into both dark matter and dark energy. On a more experimental front, the Laser Interferometer Space Antenna mission, or LISA, will be the first space-based observatory designed to detect gravitational waves. By studying these ripples, LISA could provide valuable information about the nature of space-time, the behavior of black holes, and even the very beginning of the universe itself. The detection of gravitational waves will allow scientists to observe cosmic events that are invisible to traditional telescopes, offering a completely new perspective on the universe's most violent and energetic processes. Currently under construction, the Vera C. Rubin Observatory in Chile will perform a 10-year survey of the sky, collecting data on millions of galaxies, stars, and other cosmic objects. The observatory's legacy survey of space and time will create a comprehensive map of the universe, offering unprecedented insight into the distribution of matter and energy in the cosmos. By observing the way galaxies and other cosmic structures evolve over time, scientists will be able to better understand how the universe is expanding and what forces are driving its acceleration. This information will help refine current models of the universe's evolution and potentially reveal new physics that can explain the behavior of dark energy. With observations of the universe's large-scale structure, its expansion, and the behavior of dark matter and dark energy, scientists will be able to refine models of the cosmos' ultimate end. As we look to the future, it is clear that we are on the cusp of a new era in the exploration of space, exotic physics, and the uncharted territory of universe's fate. As we push the boundaries of understanding the cosmos, some of the most exciting and thought-provoking ideas come not from well-established theories, but from speculative and exotic concepts that challenge the very foundations of physics. One of these areas of speculation involves the possibility that the fundamental constants of nature could vary over time or space. One of the key components of our understanding of the universe is that physical constants, such as the speed of light, the gravitational constant, or the fine structure constant, are fixed and unchanging. These constants govern the behavior of matter and energy, determining the structure of everything from atoms to galaxies. But what if these constants weren't constant at all? What if they could change over time or vary across different regions of space? This notion has profound implications for how we think about the universe's past, present, and future. In particular, the possibility that the cosmological constant could fluctuate or evolve over time has attracted attention. This could mean that the rate of expansion would not remain steady, and as a result, the fate of the universe could take on a radically different trajectory. If the constants of nature are not fixed, this could suggest that the laws of physics themselves could change over time. The forces that govern the interactions between particles might be different in the distant future, or the structure of space-time itself might evolve in unexpected ways. Such changes could have profound effects on the fate of the universe, potentially leading to new forms of matter and energy, or entirely new phases of the universe's expansion. If gravity were weaker in the past or became stronger in the future, this could affect everything from the life cycles of stars to the rate at which the universe expands. If gravity were to weaken over time, it might slow the collapse of matter into black holes. Alternatively, a stronger gravitational pull could accelerate the collapse of galaxies, leading to a more rapidly contracting universe. Some physicists speculate that our current understanding of physics is merely an approximation of a larger, more complex framework. If this is the case, the constants we observe may simply be the result of a local snapshot of the universe and could change over time as the universe evolves. This idea is reminiscent of the concept of a meta-law of nature, an overarching rule that governs how physical laws themselves change. Under such a framework, the universe might be in a constant state of flux, with the laws of physics adapting to changing conditions in ways that are not yet fully understood. While dark energy and dark matter dominate much of the current discourse, other forms of energy could also play a role in shaping the future of the cosmos. Some theories suggest that there could be hidden forms of energy that interact with the fabric of space-time in ways we do not yet comprehend. These energies could influence the rate of expansion, the formation of structures, or even the fundamental properties of matter and energy. One such concept is the idea of phantom energy, a hypothetical form of energy that could cause the expansion of the universe to accelerate at an ever-increasing rate. Unlike the relatively stable dark energy that we observe today, phantom energy would grow stronger over time, accelerating the expansion of the universe to such an extreme degree that all matter would eventually be ripped apart. Equally intriguing is the idea that there could be entirely new, as yet undiscovered fundamental forces at play. These forces might not be related to gravity, electromagnetism, or the nuclear forces that we are familiar with, but could operate on a completely different level. These forces could have dramatic effects on the expansion of the universe, potentially reversing the process of cosmic acceleration or even leading to a contraction. Some versions of the multiverse suggest that the constants of nature could vary from one universe to another, leading to completely different forms of reality. If this is the case, then the fate of our universe may not be determined solely by the laws of physics that govern it, but could also be influenced by the broader dynamics of the multiverse itself. Perhaps our universe will eventually end, only to be replaced by another universe with different constants and physical laws, beginning a new cycle of cosmic evolution. This idea suggests that the ultimate fate of the cosmos may not be the final end of everything, but rather a transition into something new, an ever-evolving dance of universes, each with its own rules and characteristics. Gravitational anomalies, tales of cosmic portals and wormholes. Gravitational anomalies typically refer to unexpected or unexplained disturbances in the gravitational field of a given region of space. These anomalies might show up in the way celestial bodies move, or how light bends as it passes through certain areas. A wormhole, in its simplest form, is a theoretical structure in space-time that acts like a tunnel. Imagine two distant points in the universe, far apart from each other. If space-time were bent in the right way, you could create a shortcut between these 2 points, essentially folding space in on itself. Instead of travelling across vast stretches of space, you would travel through the tunnel, bypassing the intervening distance entirely. This idea was first proposed by Albert Einstein and his colleague Nathan Rosen in 1935, who used the term Einstein-Rosen bridge to describe what we now commonly call a wormhole. According to the theory, wormholes could exist in the fabric of space-time, acting as shortcuts or portals between 2 points. The idea is still very much in the realm of speculative physics, as no experimental evidence has yet been found to suggest that wormholes actually exist. And while Einstein's general theory of relativity predicts the possibility of such structures, the conditions required for their creation would be extreme. For example, creating or maintaining a stable wormhole would likely require the presence of exotic matter, a form of matter with negative energy, which has not been observed in nature. Without this exotic matter, the wormhole would collapse before anything could pass through it. If they do exist, they could provide shortcuts across the universe, potentially enabling intergalactic travel. They could even offer a glimpse into other universes, depending on how the laws of physics play out in different regions of space-time. These theoretical portals could connect different parts of the universe, or perhaps different universes altogether. Another intriguing phenomenon that has been speculated to involve gravitational anomalies is the existence of cosmic strings. These hypothetical one-dimensional objects are thought to be incredibly dense and stretch across vast distances in space. They are remnants from the early universe, formed in the moments after the Big Bang. The peculiar thing about cosmic strings is that they are predicted to have a huge gravitational effect, warping space-time around them. Some scientists have proposed that cosmic strings could act as a sort of cosmic bridge between different regions of space-time, creating gravitational anomalies that could be interpreted as portals or shortcuts through the fabric of the universe. Large-scale cosmic voids, regions of space that contain very little matter, can cause distortions in the gravitational field of the universe. These voids are thought to be a result of the large-scale expansion of the universe, with galaxies clustering together in webs, leaving vast stretches of space devoid of galaxies or matter. These voids, while relatively empty, can still have gravitational effects on the surrounding space, bending the path of light and distorting the overall structure of the universe. Some theorists have even suggested that these cosmic voids might play a role in creating gravitational anomalies that could, in theory, function as portals or bridges through space. These anomalies invite us to think beyond the conventional limits of space-time and explore the possibility that the universe may harbour hidden pathways that allow us to experimentally test our ideas about the multiverse. Advanced civilizations as cosmic architects. When we gaze out into the vastness of the universe, it's hard to imagine that we, as a species, are the only ones capable of contemplating its mysteries. What if there were other civilizations, far more advanced than our own, with the ability to shape and influence the universe on a cosmic scale? If such civilizations exist or have existed, their technological capabilities could far surpass our current understanding, potentially allowing them to engineer the universe in ways we cannot yet fathom. The term cosmic architect evokes the image of a civilization so advanced that it could manipulate fundamental cosmic processes, even influencing the evolution of galaxies, stars, and perhaps the structure of space-time itself. This idea rests on the assumption that a sufficiently advanced civilization might not only harness the forces of nature, but also direct them for specific purposes. These beings would not simply observe the universe's natural evolution, but actively guide it according to their needs or desires. In essence, they could operate on a scale so grand that their influence could extend across light years, altering the course of cosmic history in ways we can barely begin to understand. If an advanced civilization mastered the manipulation of dark matter and dark energy, they could potentially influence the structure of galaxies or even control the rate at which the universe expands. Imagine a civilization capable of harnessing dark energy in such a way that they could slow down or even reverse the universe's expansion. Such a feat could be the result of manipulating the very fabric of space-time itself. By altering the rate of cosmic expansion, they could potentially prevent the universe from reaching a big freeze scenario. Instead, they could engineer a more stable or habitable universe, one that remains in a state more conducive to life, perhaps preserving it for trillions of years. Alternatively, an advanced civilization could, in theory, harness dark matter to reorganize or redistribute the structure of galaxies. They might choose to create new galaxies, direct their movement, or even alter the way stars form, thus shaping the universe's overall structure in a purposeful way. This kind of intervention would require technology far beyond our current capabilities, but is not outside the realm of possibility for an advanced civilization with control over the fundamental forces of the universe. A highly advanced civilization with the ability to manipulate cosmic gases and materials could seed new star systems, giving birth to new suns and planets. By influencing the processes of stellar nucleosynthesis, where elements are created in the cores of stars, they could potentially create a universe rich with the building blocks for life. They might even have the ability to terraform planets, altering their atmospheres and environments to create habitable worlds where life could thrive. But their influence might not be limited to the material universe. An advanced civilization might also engage in controlling or manipulating the very laws of physics that govern the universe. For example, they might have the ability to fine-tune the constants of nature. By adjusting these constants, they could alter the fabric of reality itself, tweaking the physical laws to create conditions more favourable for the existence of life, or more conducive to their own purposes. This kind of intervention could allow them to control the evolution of galaxies, stars, and even the potential for life across the cosmos. This brings us to the possibility of megascale projects, engineering feats on a cosmic scale that could reshape the universe. A truly advanced civilization might embark on projects such as building entire solar systems or constructing vast structures in space that could harness the energy of entire galaxies. A civilization could design and construct entire galaxies to their specifications. For instance, they might rearrange stars into specific patterns, create star systems with unique properties, or even construct artificial stars or black holes for specific purposes. They might also possess technologies that allow them to control or manipulate time and space. If a civilization could control the fabric of space-time, through the use of wormholes, for instance, they might be able to reshape the universe's structure in ways that allow them to travel through time, alter the course of history, or explore other dimensions. Perhaps they would be a post-biological civilization, a society that has transcended physical form and exists entirely in a digital realm. Such a civilization might have the capability to manipulate the entire universe through computational power or digital consciousness, existing outside the constraints of space-time as we understand it. Their influence over the universe would be subtle, perhaps operating through information and algorithms rather than physical intervention. They might exist in the backstage of reality, subtly guiding the evolution of the cosmos from a higher dimensional perspective. Time as a manipulable resource, temporal engineering. Einstein's theory of relativity already tells us that time behaves differently depending on the strength of the gravitational field or the speed at which one is moving. Near massive objects like black holes, time slows down, and at the speed of light, time theoretically stops altogether. These observations suggest that time is malleable, depending on the conditions around it. What if this malleability could be expanded to a larger scale? Could time be actively manipulated in such a way that it is not just altered by gravity or velocity, but engineered in a more precise and controlled manner? One speculative idea comes from the notion of temporal bubbles, or regions of space where time flows at different rates. Advanced civilizations, with enough understanding of the universe's underlying laws, could theoretically create or control these bubbles, manipulating the passage of time in localized areas. In such a scenario, individuals or objects inside a temporal bubble could experience time differently from those outside. This would allow for dramatic changes in the flow of time over both short and long periods. For example, a civilization could accelerate their perception of time for research or exploration, making them experience the equivalent of years or centuries in the span of mere moments, while the outside universe continues its regular pace. If time could be influenced in the right way, it might even be possible to delay, speed up, or reverse the processes of cosmic decay. If time itself could be slowed or manipulated, it might be possible to extend the life of stars, galaxies, or even the entire universe. This would create an entirely new way of thinking about the universe's fate, where rather than waiting for an inevitable end, advanced civilizations might find ways to stretch the timeline of existence to unimaginable lengths. Rather than simply passing through time as we do today, a civilization might be able to harvest or store time. Just as we store energy in batteries or use matter for construction, time could become something that is accumulated and then used when needed. For example, a civilization might accumulate time during periods when things are relatively calm, and then, in times of need, release or spend that time, perhaps to accelerate the development of new technologies or to extend the lifespan of critical systems. In such a framework, time would not simply be the constant flow we experience today, but something that could be consciously manipulated and distributed. How might such a manipulation of time work in practice? Theoretical models suggest that one way to manipulate time could involve the use of exotic materials or phenomena, such as the theoretical concept of a time machine, or the creation of closed time-like curves. These are theoretical pathways in space-time that loop back on themselves, allowing for a form of time travel. This kind of temporal engineering could also lead to paradoxes or unforeseen consequences. For instance, changing events in the past could have unintended side effects that ripple through the present and future. If time could be manipulated freely, would the concept of causality, the idea that every event is the result of a prior one, still hold true? Could altering the flow of time introduce loops or contradictions, where events occur out of order or self-referential paradoxes arise? Currently, we view time as a commodity that we cannot control. We live our lives according to a fixed schedule, constantly measuring the passage of time through clocks and calendars. Yet, as our understanding of time deepens, we begin to see that time may not be as simple as it seems. As we venture into a future where time could be engineered, we might face a dramatic shift in how we relate to it, potentially leading to a redefinition of what it means to live, to age, and even to exist. If civilizations were to one day unlock the secrets of temporal engineering, it could lead to radical transformations in how we understand life and death. Imagine a scenario where aging could be slowed or even reversed by adjusting the flow of time. If time could be stretched or compressed at will, lifespans could be drastically altered. People could experience centuries of life in a single human lifetime. Or conversely, they could skip over years, living only in the moments they choose. This kind of control over time would undoubtedly lead to ethical and philosophical dilemmas, such as questions about the value of a normal lifespan and the consequences of living beyond natural limits. Could civilizations use their control over time to reverse the expansion of the universe? Could time be adjusted to prevent the death of stars or to save dying galaxies? Theoretical models suggest that if time could be manipulated on a large scale, it might even be possible to delay the ultimate end of the universe itself, preserving the cosmos indefinitely, or at least for an unimaginable period. Alternatively, civilizations could hasten the processes of decay, bringing about the end of the universe sooner than natural laws would dictate, perhaps as an act of cosmic engineering or intentional intervention. As we continue to explore the nature of time, we might find ourselves standing at the edge of an entirely new understanding of the cosmos, one where time is no longer a relentless force that controls us, but a resource we can shape and mold to suit our desires. Parallel universes and their influence. In the quantum world, particles can exist in multiple states at once, a phenomenon known as superposition. Some scientists have speculated that this principle might extend beyond individual particles to the entire universe. According to the many worlds interpretation of quantum mechanics, every time a decision is made or a quantum event occurs, the universe splits into multiple versions, each corresponding to a different possible outcome. This means that there could be an infinite number of parallel universes, each representing a different version of reality. In this view, every moment in time might branch out into a new universe, creating a vast multiverse that contains every possible outcome of every event that ever happened or will happen. These universes would be completely separate from one another, with no way for them to interact directly. However, the very existence of such universes might still have an impact on the one we live in. For example, in the many worlds interpretation, the mere act of an observer measuring a quantum system might influence the outcome of the event, causing the universe to split. This challenges the conventional view of reality and raises intriguing questions about how the nature of observation and measurement affects the universe. Some versions of inflationary theory suggest that the expansion process could create pocket or bubble universes, each one emerging from its own localized inflationary event. These bubble universes would be disconnected from one another, each evolving independently according to its own set of physical laws and constants. Some physicists have suggested that the boundaries between parallel universes could be thin and permeable, allowing for the exchange of energy, particles, or information between them. In this view, the very fabric of the multiverse could be interconnected, with subtle influences leaking from one universe to another. It is conceivable that certain cosmic events or anomalies in one universe might have an indirect effect on a parallel universe. If, in one universe, the laws of physics were slightly different, It might cause ripples in space-time that could be felt by neighbouring universes. These ripples could manifest as gravitational waves or other forms of energy that spread out into the fabric of the multiverse. Though this interaction would be subtle, it might have measurable effects in our own universe, such as unusual cosmic phenomena, anomalous behaviours in the CMB, or unexpected deviations in the expansion rate of the universe. The fine-tuning problem refers to the observation that the physical constants of our universe, such as the strength of gravity or the mass of subatomic particles, appear to be perfectly tuned to allow for the existence of life. If these constants were even slightly different, life as we know it would not be possible. If there are an infinite number of universes, each with its own set of physical constants, then it is not surprising that at least one universe would have the right conditions for life. Our universe might simply be one of the lucky ones, existing in a patch of the multiverse where the constants happen to be just right. In this context, the idea of parallel universes challenges the traditional view that our universe is a unique and special place. Instead, the multiverse suggests that our reality is just one of countless possibilities, with each universe representing a different outcome of the fundamental parameters of existence. This shift in perspective could profoundly alter our understanding of the cosmos, moving away from the notion of a one-size-fits-all universe and towards a more complex and varied landscape of realities. If there are infinite versions of reality, each one representing a different possibility, then what does it mean for our sense of identity, purpose, or fate? In one version of reality, we might make different choices, live different lives, or even be different people. The existence of parallel universes might challenge the very idea of free will, suggesting that every decision we make leads to the creation of a new universe, each one following a different path. This idea raises profound questions about the nature of existence, consciousness, and the role of choice in shaping our lives. The idea of parallel universes forces us to reconsider the boundaries of our reality, challenging us to look beyond the confines of our own cosmic bubble and imagine a vast, interconnected multiverse that stretches far beyond the horizon of our current knowledge. What lies beyond the end of time? Does time itself have an expiry date? It seems a given that time is as permanent as the universe itself, an endless river that carries all things forward. But is that truly the case? Could time itself one day cease to exist, or could it be fundamentally altered? What lies beyond the end of time? Is there an expiry date for the very essence of time itself? While space is something we can travel through, time moves in one direction and is experienced only in a forward motion. We can't go back in time, nor can we skip forward. However, as the universe expands, we see that space-time itself stretches. The further we look into the cosmos, the further we see galaxies moving away from us due to the expansion of the universe. If this expansion continues indefinitely, the future of time could look very different than it does now. In fact, it may be that time too will be stretched to a breaking point. One possibility is that as the universe reaches a state of maximum expansion, time itself could begin to slow down. In a universe filled with ever-distant galaxies, the passage of time might feel less and less relevant. If everything becomes so spread out and isolated, the flow of time could become less significant, not only in a practical sense, but also in a fundamental one. The very structure of space-time, as it stretches and thins, could break down in such a way that time loses its meaning. Events may no longer occur in the sequence we understand, and the progression of time could grind to a halt as space itself becomes a void, devoid of any meaningful change or motion. What happens to time in such a scenario? Is it still time if no events are happening? If nothing is moving and no processes are occurring, does time lose its significance altogether? Time, as we experience it, is inseparable from the human perception of events. Time flows because we observe and measure it, and in this sense, time may be a construct that only has meaning in the context of beings that are aware of it. If life were to cease to exist, could time continue? Or would it stop altogether, as if it were merely a byproduct of living, conscious beings? This question brings us to another mind-bending idea. What if time is tied to the very fabric of the universe? Could it be that time is not just a dimension that we observe, but an active force that is linked to the existence of the universe itself? If the universe were to collapse, could this collapse result in the cessation of time? If the universe shrinks to a singularity, could time collapse along with it, ending not just the universe, but the very concept of time itself? In theories such as the Big Crunch, time would move in reverse as the universe collapsed, but would this reversal imply the actual end of time? Could time cease to exist in a meaningful way once the universe reaches a singular point? And if time does end in such a scenario, what would lie beyond it? Is there even a concept of beyond time in a universe that has collapsed in on itself? Some cosmologists have speculated that time could be cyclical. Instead of a linear progression with a definitive beginning and end, time might operate in a repeating cycle, where the universe undergoes endless phases of creation, destruction, and rebirth. In this scenario, time might not have an expiry date, but instead it would continually loop in a process of cosmic regeneration. Perhaps time, as we know it, is simply a brief part of a larger, eternal cycle, and once one cycle ends, another begins. This suggests that time itself might be eternal, without a true beginning or end, much like the universe itself. In some of the ancient philosophies of the East, the universe was viewed as undergoing endless cycles of birth, death, and rebirth. Could time too follow such a pattern? Could the end of time in one phase simply mark the beginning of time in another, as the universe begins anew with its own unique set of laws and characteristics? However, there are other theories suggesting that time, like all things in the universe, is subject to entropy. In these models, the idea of time ending doesn't mean it stops or becomes irrelevant. Instead, it might undergo a dramatic transformation as the universe approaches its maximum state of disorder. In a heat-death scenario, the universe would reach a state of maximum entropy, where no usable energy remains. In this state, no processes could occur, and there would be no change. Could this be the end of time as well, in the sense that no further moments could be experienced because everything is in a state of perfect equilibrium? Some quantum theories propose that time itself is an illusion, a byproduct of our perception rather than a fundamental property of the universe. If this idea holds true, time might not have an expiry date because it might not be real in the way we understand it. Instead, time could be an emergent property of the universe, a result of the way we perceive and interact with space-time. In this view, the end of time might not signify its true cessation, but a shift in how we experience reality. If we were to encounter higher forms of intelligence or gain access to advanced technologies, could we find a way to manipulate time? Could we extend it, reverse it, or even create new time-like dimensions? Is time a real, immutable force, or is it a human-made concept, something that only exists in our minds and our measurements? The potential end of time could take many forms, some gradual, some abrupt, some even paradoxical. As our understanding of the universe deepens, the more we are forced to confront such mysteries. What do you expect we will find at the end of time and at the end of reality? Send us your thoughts in the comments, and if you enjoyed the video, consider leaving a like and subscribing. Thanks for watching.